All right. So in order to solve kinematics problems, there are first trick is to use good frame of reference. Use good frame of reference, which means that you can switch between the frames. Okay, this is the first rule. Second rule, second trick is that in order to recover unknown quantities, what you ask to find, okay, so you can just solve triangles. From triangle, solve triangles. What I mean by that is illustrated with this problem. So first is the first trick we use a good frame of reference. So what is a good frame of reference for this thing here? Who can tell me?
Moving V over 2 to the right.
Yeah, so we go to a symmetric frame. Okay, now here is another 3 is, this is not exactly for kinematics. These are kinematics rules. Kinematics, but this is general rule. General rule, use symmetry. Use symmetry. And if the problem is not symmetric, you can make it symmetric, okay? So we go to a frame where the which moves with speed v over 2, and then you have one wheel and the other, and one moves v over 2 here, and another moves v over 2 here. So it is symmetric. Now, obviously, the intersection point moves straight up. What does this tell us? This tells us that if we go back to the horizontal first figure, then it means that the horizontal projection of velocity is 0 because in this frame. And back in the initial frame, the horizontal component of velocity is because of that v over 2. Okay, so we used a good frame of reference, and then we learned something about the velocity. That we learned that the horizontal component velocity is v over 2. And now I'm going to the point 2, and so in order to recover what you asked to find, solve the triangles. Now we know here the direction of velocity vector here, because obviously the intersection point moves along the tangent of this line here. Okay, and once it moves along tangent, so we have here. We can build similar triangles. Okay, let us make a little bit bigger. So here is radius vector 1, radius vector 2. Okay, here is half of the distance a over 2. And then here, this guy here moves up. Moves up with certain unknown speed, and we ask what is the speed. But regarding that speed, we know it's horizontal component. So this here is v over 2. Now here is right angle. This here is right angle. Okay. Now we need to just solve this triangle, find the hypotenuse while we know cosinus. And now we have similar triangles. One is this one here, and the other is this one here. Now, which angle is which angles are equal? So this angle here is the same as this angle here. Now, if Do you agree that this is the same angle here? If I make this angle here small, so this angle also goes to small. So just if we start rotating from horizontally, makes this 0, and this is also 0. The angle between velocity vector here and the vertical direction is if we imagine that this point here it's at the very bottom here. Okay. Yes, this figure actually in order to solve was not the best one, because right now in this figure it's quite easy to confuse. This and that angle here are quite similar in size, right? It's not very obvious which pair corresponds to which. So it might have been a good idea to draw a little bit make a little bit more difference between the angles of the right triangle. Okay, so we make here right now this, and then we have here the triangle for velocities. So this side here is v/2. And then now it's clear that this angle and this angle are equal, right? And so because of that, this side here is v/2 divided by sinus alpha. This is alpha. And now sinus alpha is this side.
I have a question.
By that side. Yes?
Is this v divided by 2 sine alpha or v/2 multiplied by sine alpha?
Okay, very good question.
What should be divided by, right?
What do you think?
It should be divided by, but it's not very clear from what you wrote.
Okay, so I know you guys quite often have trouble with trigonometry. Not quite often, but some of you and sometimes. So I myself, how I am doing it. So one way, in order to not to confuse between sine and cosine, is exactly what I did before right now. That I make one angle small, I imagine one angle small, and then it becomes clear. So cosine of small angle is big, and sinus of small angle is small. And so I can figure out that, okay, if I see here that, that this thing here is small, because this angle here is small and this angle here is small, then I must make it much bigger. This hypotenuse is much bigger. Okay, so so first I see that this is sine of this angle and not cosine. And second thing is that if sinus is always and cosine is between 0 and 1. So if I want the result to make bigger than it was before, I divide with it. And if I want to make it smaller, then I multiply. Here, I clearly want to make it bigger. This is bigger than that, right? So I divide by sinus. All right?
Yes.
So this is like easy and foolproof way of making sure you won't make simple silly mistake with sinus and cosine and things like that and tangent. All right?
Mr. Kader,
yes.
Here you assume that the total velocity will be perpendicular to the one of the radius.
Yes.
Why is that?
Why is that? Let us go back to the initial figure here. Okay. Intersection point moves along the wheel. Okay. Which means that it is tangent to the wheel, but tangent is always perpendicular to the radius vector.
Okay.
Mm-hmm. All right, and so it is v divided by 2 sinus alpha, and sinus alpha is this side here divided by that. So so now this here is r, and this side here we can calculate from the Pythagorean theorem. So so it will be square root of r square minus a square divided by 4 divided by r. So this is sinus alpha. And so we can write the final answer now as v total speed is the speed of the wheel divided by 2 and sinus alpha is over here. So it is v times r divided by 2 square root of r square minus a square divided by 4. And if we like, we can also rewrite it like v times r divided by square root of square root of 4r square minus a square. Okay, and here is the answer for you. All right. Now, still, these two rules are main rules to solve these kind of things. Okay.
Mr. Caldo,
Yes.
why is the horizontal velocity v over 2?
Okay.
Of
We
that-
went to the frame of reference. So we made we plan to use symmetry, makes the problem symmetric. Initially, it was
Yeah.
not symmetric. One wheel was at rest and the other was moving, but we make it symmetric by going to frame which moves with speed v over 2. And then both sides approach with speed v over 2. And then it is clear that there is this intersection point, one moves up and the other moves down. They move due to symmetry, they will not move to sideways. So in this frame of reference, the horizontal velocity component of velocity is 0. So going back to initial frame, it means that horizontal component of velocity was equal to the speed of the frame, which is v over 2. So in the initial frame of reference, horizontal component of velocity is v over 2. So this is what we say, that switch between the frames. Okay? All right.
All right.
Now I'm going to clean this because I have only one screen. Now, the size, by the way, the size of letters, it is okay. You can see nicely everything, yeah?
Yes, yes.
Okay. At some point of time, maybe I need to, if I need to write more, I might need to make a little bit smaller letters, but we'll see.
So I don't think you need to write like large text. You only need to like draw figures and use expressions, and then you can like tell us what you want to write.
Okay, I see. Depending on and how. Okay, and now goes another problem, and now we have, again, we have two wheels, but now we have one wheel, which black wheel is at rest, and red wheel rotates along this point here with angular speed omega. Okay. And now we ask the speed of this intersection point here. All right. And we have both
symmetry.
sorry?
I think it would be a good idea to use a rotating frame of reference.
Yes.
Center.
Yeah. So if angular speeds can be added and subtracted exactly the same way as velocities. So if you go to a rotating frame of reference, you can just add velocities and subtract. Okay. Now, will you try yourself to solve it?
Yes.
Is the black one moving or at rest?
Black one is at rest. Red one
Okay.
is rotating around this point here.
Okay, I think we should have like 5 or 10 to 10 minutes to solve it.
Yes. Just tell me. I am mic is my sound is on, so just tell me, and I can hear if you have something to ask or say. Okay.
Okay.
Mr. Caldo,
Yes.
do you want the speed as function of time or the distance between the two sensors?
As a function of time, let us say.
What is the starting point then? What is the point that's
Okay.
attached to?
We can also describe. Okay, let us describe by using angle. Let us say that at the moment when you have here angle alpha. Okay.
Okay.
Sir Calder,
Yes.
is the answer omega times r?
Okay. Did any of you have some success with this problem?
Oh,
I
I'm still
found that
working on
it is omega times r.
I get the same thing.
Omega times r. So,
Correlation to the alpha.
sorry?
There is no correlation between the velocity and the angle alpha.
Omega times r, you are telling me. Everyone got, tell me who got this result?
Me, I get the same results.
Okay. And who else? Who else got that result?
I'm working on it. So
Yeah,
maybe.
working. So Al-Qassem got result. Now, who got it? Hassan, you got, was it you who got?
Me.
Yeah.
Muhanna.
Muhanna. Okay, Muhanna got the same result. Okay, Al-Qassem and Muhanna. And what about Hassan?
I'm working on it. I
Okay.
think I need
Hussein?
like a few more
Hussein?
minutes.
Hussein, how are you?
Still solving.
Still solving. Sadek?
Working.
Working. Okay. So I presume everyone else, please correct me if anyone else got, but Muhanna and Al-Qassem got the result, right?
Okay.
Now, what about the rest of you? Do you want to still work on it, or you want me to show it?
Just
I want to keep working.
2 minutes only.
Yeah,
You want a little
I'm
bit
almost
more,
done,
right?
I think.
Oh, sorry?
I think I'm almost done.
Almost done.
Sir Calder,
Yes.
is there another problem?
Yeah. So you want to have another problem. Let us take that ant problem, in which case you have rope, extendable rope of length 1 meter, and then ant is crawling here with a speed of 1 centimeters per second. Okay. And then you start pulling here with a constant speed 1 meters per second. Okay, U is 1.
Again.
Okay, here is a rope, extendable rope, like a rubber string which is fixed to a wall. And now you pull this end of this rope with constant speed v equals 1 meters per second. And then you have here ant which start crawling. Okay, let me see. We can make it moving either from this end to the other end, but it crawls along the rope with speed 1 centimeters per second. And the question is if it can reach this end of the rope, and how long it will take if it can. Okay.
This problem is in the booklet, right? The one with the ant.
Something like that. Yes, I think there is. Have you solved it?
For the problem at the top.
Sorry? Yes?
For the problem at the top, I can see how I can get omega r, but I think I have some mathematical error somewhere. But I think I can get omega r if I fix it. So.
Okay. What about the others? Shall we solve it now here, or Hussein, how are you?
I think it should depend on the angle. The
So
velocity.
Hassan suggests it will depend on angle. Now, Hussein, how are you?
I solved the first problem. I'm now in the second one.
I just saw in a second. Jawad?
Yes, I'm in the second one too.
Okay, and Sadek?
The first one.
First one. Shall we solve the first one now?
Yes.
Okay. Now, guys, let us do it that way. This problem will be for everyone to continue once you are solved the other problems. We keep this, we are not going to this, but just you will be continuing once you have solved the main problem which you are currently solving. Okay. Now, but now let us go to this problem here. And so as before, we go to a frame which rotates with a speed omega. And then we can see that obviously this line in that frame is at rest, which is drawn from this to the intersection point. From the rotation center to the intersection point is at rest due to symmetry, because one rotates with omega here over 2 here, and the other moves as omega over there. And so if we go back to that frame, and then we see that because of that, this line here moves with angular speed of omega over 2. Okay? I guess every one of you probably got to that point. Okay? And now, what will be we are going to use is a theorem about inscribed angles. Because now we can see that now what is the problem is the line rotates with speed omega over 2, and we ask what is the speed of the intersection point here. Now let us say that this angle here, which is formed with this line and this line here, let this be something like beta, okay? And then beta then we have 2 beta plus alpha equals pi 180 degrees. Because this is isosceles triangle, this is beta and this is beta, and this is alpha, so sum of those angles makes pi, so 2 beta plus alpha is pi. So actually, because now if we take here time derivative of beta, beta is gives us the direction of this blue line here. So beta is obviously the angular speed of the blue line, which we know is omega over 2. Now, if we take from this equation here time derivative from left hand side and right hand side, so right hand side derivative goes to 0. So you obtain 2 beta dot plus alpha dot equal to 0. But 2 beta dot is 2 times omega over 2, and this equals to now minus alpha dot. And so this, of course, equal to omega. So you can see that actually this angle here, alpha, changes at the rate of omega. So this line here, now maybe I make it like black line, for instance, here. So this line here rotates with angular speed of omega. But this is a radius vector. So if this rotates with speed omega, so this intersection point, of course, moves with speed, radius times omega. This is the speed, v. Okay. Everything fine with that now?
Teacher, beta prime, beta dot. Why is it omega over 2? Again, please.
Okay, because we learned that this blue line, which I drew here, this line here, this rotates with angular speed omega over 2. We learned this by going to a frame which moved with omega over 2, and so it was rest in that frame, right? So this line here rotates with omega over 2. But this line and this radius vector form angle beta. So if this rotates with omega over 2, so the changing rate of angle beta is omega over 2.
Okay.
All right. So beta dot is omega over 2. Everyone happy?
Yes. But can you repeat the second problem?
Now I am not going to repeat, but I'm going to we are moving like this. This problem here is independent problem, which just for exercising for those of you who have finished the main problem here. I'm not going right now to tell this, but we're going to take next problem.
Okay.
Yes.
I found an answer for the exercise problem.
Okay.
100 seconds.
And what is your answer?
100 seconds.
100 seconds.
Yes.
No way. No way.
I found that it will not reach, I think. Not sure.
Both answers are wrong. It will reach, but and it is not 100 seconds.
I found a differential equation, but I don't know how to solve it.
Yes. And what did you get?
It's like the derivative, and I don't know like how can we solve the derivative from the equation. So
Okay. Let us keep. Today, once we finish today, we are going to solve this. Okay. Not before. All right.
Okay. Okay.
Okay.
Can you re-explain it so that if we finish your problem early?
Yeah. Okay. All right. So now, next problem up is that problem like that. So you have hinged construction here, and this point here moves with speed v, and we are asking the speed of this point here, which point we'll take. We take this point here, okay? We want to have a speed u of this point here and acceleration of this point here. We want to know both u and acceleration a of this point here. All right? And side length is this is a, this is 2a, this is 3a.
Mr. Khaled,
Yes.
This problem actually solved before with you, but I don't know, like if there are some people didn't solve it, okay. But I solved this before.
Okay, if you are sure how to solve it, you have still problem here.
Oh, okay.
So you are going to solve the red.
Yeah, so those of you who don't know how to solve red, please solve red. If you don't know how to solve red, then please solve this.
Okay.
Now tell me, how many of you are going to solve red? Tell me red if you are solving red.
Right.
Right.
Okay. All right. Then do you want to have again a few minutes? Okay. Please tell me once you have got speed u, because calculation of acceleration a is involves a few more tricks. So once you have solved u, then we are together solving a, and then I give you one more problem. All right. So once you've got speed u, tell me. And just here angle is 45. This is 90 degrees. You asked about u and a at the moment when this angle over there is 90 degrees.
What is the length A and 2A and 3A? Are they the distance between
this
the hinges?
side length is A, this is 2A, this is 3A. And this is hinged structure.
And so every section has the same length.
This is bar, and this is hinge. So it can the angle can change between this and that. Okay.
Yeah.
And here is the same thing. Here is hinge.
And so the distance between
sorry.
So the distance between after A, the first one.
Yeah.
What about the second one between the end of A and the start of the hinge? Is that also A?
Yeah. So this is A. This is A. This is A. This is A. This is 2A. This is 2A.
Okay.
This is 2A. This is 2A. Now this is wall which is fixed. This is hinge. This is hinge. This is hinge, and this is hinge. And see here, these are also hinges. A lot of hinges. Okay.
Mr. Calder.
Yes.
In the blue problem, where was the ant initially?
Once again.
In the blue problem.
Yes.
The ant initially where it was.
At this end here, at the free end, and it starts scrolling from left to right.
Oh, okay.
Someone wanted to ask something? No?
Teacher,
Yes.
is the horizontal will be V over 3?
Horizontal speed is, I think, horizontal, let us see, it is always at the distance of 5 from this end and always at the distance of 4 at this end. So it is 4 over 9. Did you say like that? No, wait. Okay. So we have here 2 plus 4 plus 6. 12 overall, right? Yeah, 12 overall. Now, from until this line, we have 2 plus 2 is 4. So it is the horizontal speed here is 4 over 12 times v equals v over 3. Okay, horizontal speed 1/3 of v. Does it make sense?
I didn't find it yet.
Okay. Well, you can of course also try going to reference frame, but probably not right now yet, because if let us say this distance horizontally to here is x, then to here is also x, but to here is 2x, and from to here is 2x, and to here is 3, to here is 3. Okay, so all together, this coordinate here is 1 plus 1 plus 2 plus 2 plus 3 plus 3. Overall, 12x is horizontal coordinate. And if we take derivative, we get v. Okay, so x dot equals v over 12. Now, this point here has horizontal coordinate x plus 2x is 4x. So speed here is 4x dot, which equals 4 over 12 times v equals v over 3. Okay?
Yeah, okay. Okay, that's for the horizontal vector of...
Yeah, this horizontal component of velocity.
And now we need to find the vertical one, which I
Now
don't think
you
will
need to
be
write vertical, yes.
Vertical velocity of which point?
Sorry?
Of which point? Vertical velocity.
This point here.
Okay.
do we even need the vertical velocity, or can we just use trigonometry to find the velocity?
Well, now you learn the tricks. You can switch between frames, and yeah. So there are maybe there are more than one way, but yeah. Have a look what you can do.
Just a moment.
Yeah.
Mr. Calda,
Yes.
is the vertical component is square root of 2 over 24 times v?
What did you tell? Vertical component?
Square root of 2 over 24.
24 times v. I don't know. Let us wait a little more for other guys, and then we'll do it.
Teacher,
Yes.
I got v over 6. No.
V over 6. Okay.
Over 12, teacher, not 24.
Sorry?
Over 12, not 24.
Over 12. Okay.
Mr. Khalda,
Yes.
I got V over 6 also.
You got how much? V over?
V over 6, the same as.
Okay, V over 6. Okay. All right. So, and this is vertical component. All right. So, shall we do it together? So, what we do is we go now. What we can do is we go to the frame of reference where this point is at rest. And in that case, the horizontal projection of this velocity is 2x. Okay? I go to the frame where this point is at rest, and then this point now distance from this resting point in our new frame to the horizontal projection of this point is now 2x. So it's in this frame, v prime x component is 2x dot, but our x dot was v over 12, so this is v over 6. Now, this is the horizontal component, but it moves here, it rotates, moves along circle because the distance to this point here is fixed by the length of the rod. And so, because here is 45 degrees, velocity is under 45 degrees, Vxy prime equal to Vx prime equals V over 6. But our frame was moved horizontally, so there was no change in the vertical component of the velocity. So vertical component of velocity is V over 6, as many of you correctly noted. Okay? Is this clear to everyone?
Okay. Yeah.
Now, and now we...
before
yes.
that, actually, I have a question. So what you did is that you took a frame of reference that is moving with the first hinge, and that way,
yes,
the point that we want is moving in a circular motion.
Yes, yes, yes. So
Okay, yeah,
remember the rule. Always you can switch between the frames. Yours the best frame.
Yeah.
Okay. And now we have we know the components. One component is v over 3, other is v over 6. So now we can calculate the total speed, which is now
in this frame, when you go to that frame,
yeah,
v prime equals vh prime. Is it because the angle is 45?
Yeah, because
or why?
Because now in this frame it rotates along circular motion downwards under 45 degrees. Okay, so if velocity is under 45 degrees, the projection horizontal and vertical are equal, right? One is v times cosine 45, and this is sinus 45, but these are equal.
Okay.
Yes.
I used another method, but it gave me a wrong answer. I said that x squared plus y squared is constant, or is a squared, okay? I named the vertical length as y.
Yeah.
So we'll have y, 2y, 3y, right?
Yeah. So you did something like that. This is also a valid way of doing it. You can say that, okay, let this be, now x is already used, let us take y and z. So this is y, this is z. Okay, now we have y square plus z square is y square plus z square equals 4a square. Now we take time derivative here, and we obtain 2y dot plus 2z dot equal to 0. So from here we obtain that y dot divided by z dot equals minus z divided by y. But because z equals to y at this given moment of time, so this is minus 1. So again, we obtain the same results that horizontal and vertical velocities are equal. One is y dot, the other is z dot. All right.
Teacher, y is the same as 2x here.
Sorry?
Y is the same as 2x.
Yeah, y is the same as 2x, yeah. All right?
Yes. Okay. Now it seems simple.
Yeah. Now, okay, let me clean this because I wanted to do something else now. So to finish the problem, I have now v is square root of, and now we have horizontal component of it is v over 3. So v square, okay, this is u, not v, but u. V square, it was divided by 3, divided by 9, plus now this v over 6. So it is v square over 36. And now this we need to calculate. So we can 1/3 bring v over 3 bring before the braces, and here remains 1 plus 1 over 4 equals v over 6 and square root of 5. Okay, is the speed. Well, that was a simple part, but actually there is one more way of solving this problem. And this is by using instantaneous center of rotation. Instantaneous axis of rotation. Now, let me clean this part here. And yeah. So if we have a rigid body, then the motion of rigid body can be considered as rotation around instantaneous center of rotation. What does it mean? It means that the velocity vectors are the same as if the body rotates around the instantaneous axis of rotation. So let us say that if you have here a center of rotation, then all the velocity vectors are perpendicular to the radius vector, because it's like rotation around this point here, and speed is proportional to the distance. Okay, so like that. And which means that angles are equal. This is if this is R1, this is R2, so V1 is R1 times omega, V2 is R2 multiplied by omega. So we have like a similar similar triangles. Tangents are equal. Tangent alpha in the figure would be V1 divided by R1. V1 divided by R1, and alpha 1 equals omega, and tangent alpha 2 is also omega. Okay, now this means also that if you have a rigid body and you know the velocity of 2 points, okay, velocity of 1 point and the direction of motion of the other point here, then you can reconstruct the instantaneous center of rotation by drawing perpendicular. So from this point, center of rotation is in the perpendicular direction, and from this point it is also in the perpendicular direction to the velocity. So here is now the instantaneous center of rotation. This works as long as these two velocities are not parallel to each other. If they are parallel, then you need to know a little bit more. Then let us say you have one point here and another point which is parallel. If it was here, it would be impossible because instantaneous center of rotation would be in the perpendicular direction, And if you take here perpendicular and here perpendicular, they would meet at infinity. So you cannot have something like that. It means that in that case you would need to have, if instantaneous center of rotation is at infinity, then it means that you have translation motion, which means that these velocities need to be also equal in magnitude. But if they are different in magnitude, then this point here needs to be, if the velocity here is smaller, it would need to be closer to the center of rotation. So they cannot be like that. But they can be on the same line. So if velocity here is v1 and here is velocity is v2, then you just draw a line which goes through the endpoints of these vectors, and here where it meets with this line here, you have an instantaneous center of rotation. Okay, is that clear to everyone?
Clear.
Okay.
Yes, yes.
Now we can use this approach to actually to solve also answer the question here. So the question was, what is the speed of this point here? Now we can figure out what is the instantaneous center of rotation for this this bar here. So for this bar, where is instantaneous center of rotation? Now we know that this point here with a hinge at the hinge, this moves horizontally, right? Velocity here is horizontal. Perpendicular is here, lies on this vertical line. Okay. So instantaneous center of rotation must lie on this line. Agreed?
Yes.
Why though?
Because this point here, the point at this bar here, which is at the axis, this moves horizontally due to symmetry.
Oh yes, because okay, because the horizontal velocity is the constant. Okay.
Yeah. Yes. Yes. So this moves horizontally. Now, and we draw a perpendicular, which is vertical. Now, this point here moves tangentially, which is along the bar itself. And now we draw perpendicular to it, and because here is 90 degrees, so perpendicular goes along this line here. So here is instantaneous center of rotation. Okay.
Teacher, how can we know this is going to be the velocity to the range on the hinge?
Once again, how do we know that velocity
Is parallel to the red line?
you mean this point here?
Yes, yes.
Okay, so this moves tangentially. It moves under 90 degrees with respect to the bar, because this is the end point of this piece of bar, right? It rotates along this point here.
Okay, okay.
Yeah. Okay. All right.
All right.
So, yeah. And now we know the speed of this point here, and we want to know the speed of that point here. The speed of this point here, now what was it? V over 3, was it? Yes, V over 3. Okay. Now we know that the speeds relate as the distances from the instantaneous center of rotation. So you need to calculate distance B from here to here and distance C from here to here.
Isn't it V over 6?
Sorry?
Isn't it V over 6?
V over 6, I think. V over 6 was the speed of this point here related to relative to this point here, but yes, this point here. You're right. This point here is V over 6. Yeah, you're right. Thank you very much. This is V over 6. This is 2
Okay,
divided by
teacher.
12. Yeah. Sorry?
The upper point, the perpendicular to the velocity, where will be?
Once again?
The upper point,
Yeah.
where is the perpendicular?
To the line drawn from the instantaneous center of rotation. It is perpendicular to this line here, okay?
Okay.
And now we need to calculate B and C. Now, what is B? B is B is I guess well, who can tell me what is B? B is I guess A times square root of 2. Is that right? Yeah, A times square root of 2, I think. Is that right? Because this is A and this is A. Okay? This length here is A and this length here is A. And so this length here is square root of 2 times A. B is square root of 2 times A. Am I right?
Yes.
And C is now have right triangle. This is A and this is 3A. A and 2A. C is square root of A square plus 9A square equals A square root of 10. And so U equals V over 6 and multiplied by square root of 10 divided by square root of 2. This stands for C and this stands for B. And all together, this equals V divided by 6 and square root of 5. I think we got the same result before. Okay? Everyone happy?
Mr. Calda, can you write what is B and what is C?
Sorry? C is, this length here is C. Let me make it blue, then it might be better for you. So the blue line is C. Okay, this is C. And B is this line here. Let me make this B also blue. Okay, this is B. Distances from the instantaneous center of rotation. All right.
Mr. Calda,
Yes.
how can we have an angle between two vectors that don't have the same unit?
Once again, how can we?
Like you write tan alpha equal to V over R. But how can we have such thing? Like the angle combine two things that don't have the same unit.
You mean here? Yeah, well,
Yes.
the thing is that here in the figure, of course, when I draw here velocity vector. Velocity vector is not comparable to the distance because this distance is measured in centimeters, but this is measured in meters per second. This is in meters, this is in meters per second. So actually, you can draw arbitrary scale here for the speed. So it's valid to draw that way, but it would be also valid to draw that way. Because before I draw the first velocity vector, I have no scale for v. But once I draw one, then we have given scale of scale v. And now, but once I decided on the scale, then I can consider this mathematical like a triangle and calculate things, tangent alpha. And this will be now omega, which is kind of not very good because we expect tangent to be dimensionless. But then again, because we did not have scale and we could draw this shorter, longer, we can see that tangent can also, on this figure, can have different lengths, different values for the angle. So, this is not very good, does not look very nice, but it is still okay if you know what they are doing. We are writing here tangent knowingly that this will be dimensional, which means that depending on what scale you use for velocity, we'll have different values for the angle, for the tangent.
So whatever scale we use, we will end up in the same intersection point.
Yeah, intersection point will be the same. So if I had little different scales, then my angle would be different, but these two angles are still equal. So when I use scale as given by red vector, then I have the red angle here. If I draw use this scale here, I have blue angle. Angles are different. Red angle is different from blue angle, which is because we have dimensional value here. This is not dimensionless, but dimensional. That's why you have angle depends on the scale you use for velocity. But in both cases, these two angles are equal. That was the important point here.
Okay.
So Kalda,
Yes.
from where did you calculate the value of b?
B is, we have this right triangle here. We have this right triangle here. This length is A, this length is A. Here is right angle. So Pythagorean theorem, square this plus square this and square root.
Okay.
Mr. Kalda.
Yes.
So I have a question, but it's not related to the problem itself.
Okay.
It's related to the schedule. So, so we have a 5-hour session that's continuous, right?
Yes.
So I think it would be a good idea to have breaks in between so that we don't get burned out, like a 15-minute break in the middle.
Yeah, I think so too. But how many breaks in between you want to have? So because we have still is one break okay, or would like to have 2 breaks?
There need to be prayer breaks. So.
Okay, so the prayer break is at which time?
5:30.
I'm not sure because yes, 5:30 for sure. 5:30.
5:30. So right now.
احنا في الرياض عادي.
Sorry.
For me, it would be like 5:10 or 5:15, but since he's in a different region, it's like 5:30. I don't know about
5:30. 5:30 is first break.
Yes.
5:30 is not okay.
And okay, this is right now. We are going to make then 15 minutes break. Is that okay?
What about 5:40? It will be better.
5:40.
Yes.
Yeah, 5:40 because for Qasim and other people in the eastern region,
So we make
they start later.
5:40.
The western region. Yes.
5:40.
5:45 to be okay. That's okay.
No. All right.
That's perfect. That's
Okay, we'll take this break and then we'll see if we need one more later.
Yeah, and then another one at like 6:40 I think.
Okay.
ليش
Right,
تصلي بعدين ما في مشكلة.
Sorry?
الساعة 9.
9.
6:40.
خلاص يا حسن.
Okay, never mind then.
One enough, I think.
Okay.
One break is enough.
Okay. All right. Then we have still 4 minutes or so to go, and now are you all happy with that problem thus far?
But wait, what time is it for you?
5:36.
It's 6:36 for us. So for you, the break would be like 4:40 too.
We missed 1 hour actually from
Sorry?
today. We missed 1 hour from today, so
Oh.
that's the.
I was thinking that we are living in the same time zone, but it appears we are not in the same time zone.
I think maybe because in the winter, usually
Right.
Western
Yeah,
countries change the time.
winter, yeah. And then you would like to finish today at 9 o'clock or 10 o'clock?
9 o'clock.
9 o'clock. So we finish 9 o'clock and we take a 1 hour lesson then.
So for you, it would be. Wait, because I don't know, because it's a different time zone. So the schedule is 4 to 9, but we don't know if that's for us or for you. So for us, we were ready at 4, but there was no meeting.
All right.
At 4 for us,
Yeah,
but it was
actually, yeah.
3 p.m.
Actually, yeah. As for the meeting was that. Did you get the link to Zoom? Probably no, because I sent to Talal and Mate, but then it appears that Talal had a different email. Well, his Hotmail was not working or something like that. He did not receive my email with the Zoom link, and then that was what happened. Why we were unable to start it earlier. But then again, also I was like thinking that we have in the same time zone, and my time zone right now tells me it is 5 o'clock. Yes, 5:50, 5:40.
So when will the meetings actually be on a day-to-day basis?
The time schedule which I gave you, I had in mind actually my time zone, because in some cases we might change it because well, it is okay today and tomorrow, and in some most days it's probably okay, but in some days we might think maybe a little modification to the schedule. But anyway, so today, tomorrow we can start 4 o'clock in your time zone. So we can finish 9 o'clock in your time zone tomorrow, okay? So
I don't mind if it's just 5 to 10 for us. So like just the normal one.
You don't mind if it's 5? I would prefer 5 to 10, yes. But now it depends if every one of you is okay with that.
Please, 4 to 9.
Just for today to compensate the hour that we missed.
Okay, let us do today, just today, from we finish 10 o'clock, but in also the other days, we finish at 9 o'clock, but there might be one day or two when I need to ask you to finish it earlier, because I think I have I have obligation on let me see, on Monday I need to I cannot start at 4 in your time zone. Monday is also when we would need to start at 5 o'clock.
So it's only one day, because we have 5 days.
I have Monday. I have okay. So today in your time zone 5 to 10. Now Monday.
Saturday, Sunday.
Monday also from 5 to 10. But in the other days we have from 4 to 9. Let me see, Monday, Wednesday, just let me go through the, yeah, I think it should be okay for the other days to have from from 4 to 9 for me. Okay.
Okay.
Other days. Other days. And maybe
because we have today, tomorrow, and we have 5 days together, I think.
yeah.
And the 5th day is a test.
Yes.
So actually, a question about the test.
Let us keep that mostly, and now when it should test is. I have one more problematic day. Is also Thursday. Is Thursday test day or not? But it's maybe it's okay. Maybe it's okay.
Let me check the schedule.
It's on Wednesday.
Test number 1 is on Wednesday, so we won't even be together on Thursday.
Okay. All right. Yeah, Thursday. We won't be together. All right. Then no problem. Then no problem. That's what what you are seeing here. Okay. Today.
So regarding the test, actually.
Sorry.
On Wednesday, it says that there are 2 sessions.
Yes.
Test number 1, and it's going to be from 9:30 to 12:30.
Yeah.
And then from 2 to 5. So it's like 2 sections.
Yeah, but this is test, right?
Okay. So
yeah.
you won't be there, okay?
Yeah. So, I don't know how we are doing your test because are you going to we'll give you the problems which you solve, and then there is no supervision of you how we are solving. It's not decided yet how we shall do, because during the European Olympiad and Nordic Baltic Olympiad, we had like you need to switch on your Zoom, and then we'll follow what you are doing. We can do that way as well. In that case, I can kind of try to.
We will not cheat. Like this is like training, so we won't.
Training. So it is not so strict. Okay, yeah, I agree. That this is not competition, this is training. Yeah, I agree. So there is no
it's
need
not a team selection test, so
there is no need to have a look how you solve, but you should have probably opportunity at the beginning, at least during first 1 hour or so. I think we should give you opportunity to ask questions regarding problems. So we keep maybe Zoom session on during the first 1 hour, something like that.
Teacher,
Yes.
on Tuesday, what did you say about Tuesday?
Tuesday as scheduled. Tuesday as scheduled from 4 to 9.
Okay.
Today from 5 to 10, on Monday from 5 to 10, all the other days from 4 to 9.
Okay.
All right?
All right.
okay.
And now, shall I move on with this problem here?
Yes.
Okay.
Can we have a quick break? Because we just finished this problem. So like 5 minutes, something like that, just to go get water and
But you had this break here.
Yeah.
But we didn't have the break.
Oh, you didn't have break. And now it's okay. Yeah, you did not have break. Okay, I agree. Okay, let us make because you did not have breaks, and let us make now. Yeah, I agree.
15 minutes, right? Not 5.
15 minutes break.
Okay.
I have something.
Sorry.
I have something I want to tell about the problem before the break.
Yeah. Okay.
Here, can we use this instantaneous axis of rotation to find the acceleration just like circular motion?
No. No. This is a very important point. That actually instantaneous center of rotation you can use only to find the velocities, speeds, but not you cannot use it for centripetal acceleration, because the instantaneous center of rotation can move, and if it does so, then this formula is no longer valid. So instantaneous center of velocity is only for velocities, not for accelerations. Okay.
Okay.
Okay, so 15-minute break.
Yeah, 15 minutes break.
Okay, see you.
Yeah, 6 o'clock. We meet 6 o'clock, right? No, see, I again confused with so 7 o'clock in your time zone, right? 7 o'clock in your time zone.
Right.
Right now, 17:46 in my clock, 18:46 in your clock. So 19 will resume in your time zone.
What? What did you say?
Now we have 18:47. Is that right?
Yes, yes.
Okay, now break until 19:00. Break. Okay. How are you? Are you back?
Yes.
Okay. So now how to find the acceleration? In order to find acceleration, I proceed quite in the same way, that by knowing components of acceleration, we like figure out what the modulus is. So first thing is that we know horizontal component of acceleration. So who can tell me what is horizontal component of acceleration?
0.
0, yeah, because independent of angle, it moves always with the same speed v over 3, the horizontal projection. So there is no horizontal acceleration, which means that acceleration is strictly vertical. So acceleration is strictly vertical, and along this line here is acceleration, and up or down I still need to figure out. But then what else do I know? Do I know some component of the acceleration? So we can calculate acceleration if we have circular motions. Then we know this is centripetal acceleration, and we have also tangential acceleration. So we know that if we have a rotational motion along circle, then we have centripetal acceleration is v squared divided by r. And tangential acceleration is angular acceleration multiplied by radius. Well, now typically this we still don't know. Angular acceleration usually is like question in itself. So the second formula is not very useful, but this usually it is easier to calculate because like here we know already the speed, we know the distance, and then we can calculate centripetal acceleration. So if it moves along circles, then we can figure out what is the centripetal acceleration. And then once I know the direction, and right now we know the direction is up-down, right? So we know the direction, and we know that there is some tangential along this line, some tangential, and non-centripetal. Then we can figure out what is the modulus, because we know that it is vertical. So the figure looks like that. We have centripetal acceleration, we have tangential, and the result must be vertical. That's what we know. Okay?
Okay.
Now,
Find the angular acceleration, because here we have angle 45.
yeah. Now we have 45, so it is 45 degrees here, and so it is quite easier because of that. So so now we go to a frame where it moves along circle, which is a frame of reference of this joint here, and then it moves in that frame. It has a horizontal component v over 6 and vertical component v over 6. So in that frame, v, okay, let us use it now u, because v is, okay, u is square root of 2 multiplied by v over 6, because it has horizontal v over 6 and vertical v over 6. Overall, square root of 2 times v over 6 is a speed. And now centripetal acceleration, because of that, is u square is now v square over 18, and divided by the radius of the circle, it is 2a and 2a. Okay, so this is v square over 36a. Is the centripetal acceleration. but overall acceleration is square root of 2 times larger because it is hypotenuse. So A is square root of 2 times AC equals square root of 2V squared divided by 36A. Okay?
Okay.
Oh, well, now we have a little bit problematics at A, and here is A. Just keep this is acceleration, this is length. So a little bit problematic, but please don't start solving here with respect to A, because this A is not that A here.
Clear.
Okay.
I have a question.
Yes.
Why didn't we just find the acceleration inside a reference frame, and then it will be the same as the real acceleration? Like if we took the
That's what we did. That we did. We went to frame where this point is at rest, and we calculate there. But because our frame moved translationally, so acceleration there equal to acceleration in lab frame. That's exactly.
what do you mean?
Sorry.
So it's just going to be like so the acceleration is just going to be v squared over 2a, which is like r.
Yeah.
Okay, because we did something else before that to calculate. Like we didn't use a reference frame in the first solution before the break.
We did not use when we calculated the velocities, but now we were calculating acceleration.
Oh, okay.
All right.
Can't we calculate the centripetal acceleration from the instantaneous center of rotation directly?
So everyone happy with that now?
I have a question.
Shall I take the next problem?
Yes.
Okay, let us take the next problem. Yes.
Can you, when you give us a problem, give us the source of it? Because I need.
You want to have the source of the where the problem is taken?
Yes, I want to know from where. If it is possible.
Yeah, I think this problem, well, it is from the booklet, but originally it was the final round of Physics Olympiad of the former Soviet Union. It was from a fairly big competition, actually.
Yeah, I know this problem from the booklet. I mean,
but originally I was telling that originally it was a final round problem from former Soviet Union for quite a long time ago.
Okay.
Yeah. All right.
Mr. Calder.
Yes.
Can't we in this problem use directly calculate the centripetal acceleration from the instantaneous center of rotation?
Well, I mentioned that I told you that you cannot use instantaneous center of rotation for calculating accelerations. You can use this only to calculate velocities, but not accelerations.
Okay.
Okay, now, you know what is cycloid? Cycloid is when you take disk, mark a point on it, and let the disk roll on the surface. And the cycloid is the trajectory which is drawn by this marked point. So it goes something like that. Okay, this is cycloid. Now my question is, if we take a cycloid, which height is h. Now, what is the curvature radius of here? Curvature radius. Can you tell me what is the curvature radius of this trajectory? This is the next task, and now there is no source for this problem because I don't. It might be somewhere, but well, problem with no source. Okay.
What is the problem? Can you repeat?
Curvature radius of the cycloid at its topmost point is a question.
And what we are given?
A cycloid which has height h. So what is its curvature radius?
So what is happening in the problem? What is happening?
Okay.
What is like?
First, I explained you what is cycloid. Cycloid is a curve. What you will obtain if you take a disk or a wheel and mark one point on the wheel, on the disk, and then you let the disk roll on the surface, on the solid horizontal surface. And then the trace of this marked point, the trace which it draws, this is called cycloid. Okay? This is called cycloid. And now I am asking, what is the curvature radius of the cycloid at its topmost point if the height of the cycloid is h? This here is height. Okay.
Is
Yeah.
it 2h? 2h.
2h, yeah, but why? How did you solve it?
Centripetal acceleration.
Yeah, okay, yes, entirely correct. So we can, how we solve it, we go to reference, let us say that the wheel of radius r rolls with speed v. So we have omega, yeah, so v, and then we go to the frame which moves together with the wheel, and then in that frame we have a centripetal acceleration is v squared divided by r on the one hand side, okay, r capital, not r small, but r capital on the one hand side, and on the other hand side, now in lab frame at topmost point it moves with speed 2v. So on the other hand, it is 2v squared divided by curvature radius. So I know that this acceleration must be the same because our frame was moving with translationally with constant speed. So here we can conclude that r equals 4r capital, but r capital was 2r capital was h, so it is 2h. All right.
All right.
Sorry?
All right.
Okay, so okay, so I understand the solution, but for the next problems, can we go a little slower? Because for this problem, I was still comprehending the problem itself when we started.
Some guy just threw out the answer, so I wanted. I just went with that.
Yeah.
Don't worry. Next problem, we'll take it slowly.
Yes.
Okay. Next problem, we take it slowly, and the next problem is from the booklet. And we have a hinged structure. So we have two bars connected with hinge here. And this endpoint here moves with constant velocity v, so that the distance here is real. And now we ask what is the acceleration of this point here. Acceleration. First, when first when we have this link here is horizontal. First link horizontal. And second, when the first link is at its reverses its angular speed. So when angular speed is of the first link is 0. So acceleration of this joint point here in two cases. First, when the first link, left link here is horizontal, and second, when the first link has 0 angular speed. Okay?
So, do you mean that the first hinge will stay horizontal?
Yeah, this moves constantly with constant speed, velocity v along this dashed line. And you ask acceleration of this point here at two instances, two moments of time. First moment, and when this link here is horizontal, and second instant is when first link has 0 angular speed.
Sure.
Yes.
Isn't the second case when the velocity of the connection point is 0?
No.
Once again?
No, nothing.
I think the first case is very easy if you notice something.
You think it is very
detail.
easy? Are you sure it is very easy?
Maybe intuitively.
I don't think it is very easy. So now please try to do it yourself, and once you are finished, then please let me know. Or if you give up, then also let me know.
So, Calda,
Yes.
I got an answer for this one. It is 2v squared over L.
Once again?
2v squared over L.
I don't think it is correct.
I think it's just v squared over 2l.
Also not correct.
Okay.
The problem
So why?
is not as easy as you believe. I don't think, yeah, it's a little bit more difficult than you think it is.
Mr. Kada, I solved the first part.
And the answer is?
I got v squared divided by the square root of 3 times L.
Yeah, that's more like that, more like it. That's better. Okay, then so you can continue with the second part.
I have a question.
Yes.
What does omega refer to?
Angular speed of the left link.
Okay.
Mr. Calda,
Yes.
for the second part, is it twice the first part?
No.
Okay.
For the first part, is it b square over 2l?
E squared divided by square root of 3l. I think C is correct answer, yeah.
Mr. Khaled.
Yes.
In the second part, if the first hand doesn't rotate, then what is the difference? The same problem.
Mhm. If the second angular instantaneous angular speed is 0, then it means it is going to reverse its direction, right? It was like it goes like that and then going back, right? Which position is then the right link at that moment? Okay, it starts from here and then somehow goes here and then going back. So at which position is rightmost link at this moment when the left link is reversing direction? It is on its extreme position before turning back. Goes that way and then turning back. What position takes right link at that moment of time? Can you tell me?
Horizontal.
Yes, horizontal, yes, exactly. At that moment, it is horizontal because then the left end extends to the, as far as possible. If left end is as far as possible, this link takes extreme position, right?
Yeah. So it will be the same as problem
Yeah, the
1.
same answer, because now we can actually go to another frame. We can go to this frame where this point is at rest. The frame which moves with constant speed, and then but then this one moves down. And then we asked about acceleration at the moment when this link is horizontal. It's just the same as the first part, right? Can you see it?
Yes, I can see it.
Yeah, second part is actually exactly the same as the first part, because if you go to a frame which moves with speed v up, then this moment here corresponds to the right link is horizontal, which is like corresponds to this case here before. Okay, now tell me who has not yet obtained this result here, v squared divided by square root of 3l.
Me.
Who? Which
I didn't.
Ahmed?
Hassan.
Mukanna?
Hassan.
Yes, I didn't.
So shall we do
It's
it
me
here
also.
together?
Yes.
Yes, yes.
Okay.
Yes, because I am lost.
And those who are already fine, you can continue working on the program. Okay. Now we have a link, left link is horizontal. And then this here moves up. This here moves up. And now if this is 2L and this is L, then this here is 30 degrees, right? And this moves up with V. And now, actually, there is also one thing which I did not mention you, but this is still also useful. If you have a rigid body and you have 2 points, and you then you have speed here v1, and here you have speed v2. And now you connect these 2 points with a line, and then you have here alpha and beta. Okay, beta and alpha. Okay, maybe alpha 1, alpha 2. If we have indices, then maybe alpha 1.
We know it.
Yeah, okay, so this is alpha 2, and here is alpha 1. Then we have v1 cosine alpha 1 equals to v2 cosine alpha 2. Projections are equal because otherwise the distance will start changing, right, between these 2 points. And here you can apply.
Oh, yes.
Yeah, here you can apply this stuff here in this case. So first thing to notice is that this point here moves along circle, right? So at this moment, the velocity is vertical. Okay.
Yes.
Now, if continue, angle here equals to angle here. Projections must be equal, so speeds must be also equal. So from this condition, I immediately conclude that this speed here is also v. Okay?
Yes.
Okay. All right.
Question.
Yes?
How it will be vertical?
Why vertical?
Sorry, how?
Because it moves along circle.
I mean, why it's not down?
Because this moves up.
If it was down, it would be
If
like if you look at the rigid body.
Compressing. It will start compressing the rod.
Yes.
Okay.
Okay, so moving on from this, we know that if we look at the first rod, we know that the point will be rotating and it will have a centripetal motion around the point.
Yeah. Okay, now we know.
And then we have.
Now we know here it has got centripetal acceleration. C equal v squared divided by 4L, 2L. Okay. This way.
Oh, but there will also be a tangential component. Okay.
Yeah, but there is tangential component. But no worries. So now we know one component of the acceleration. Do we know the direction?
I think if we take what's it called? If we take a reference frame moving with the moving point, which is moving with v, the right hinge.
Yes.
Then in that frame, the point must also be in. So it's like centripetal motion. Oh, circular motion.
Very good. So we go to frame by this at rest. So now it would rotate along that point here, but it went to frame which moves with v up. So in that frame, the speed of joint is 0, because according to additional velocities. Yeah, it has 0 speed, so it means that it has centripetal acceleration 0. AC prime equal to 0. V squared, v is just 0. V squared divided by radius is 0.
In that case, I think that we can conclude that the acceleration is going to be parallel to the second rod at this moment.
Yeah, so centripetal acceleration is a projection of the full acceleration to the radius vector. So if projection is 0, so acceleration is perpendicular. So here is our direction of the acceleration. So
why is it?
And the projection gives us this thing here. So here is right angle, and no, wrong. Now I did it wrong. So,
can you repeat that?
So the other way around it is. So okay, the direction of acceleration is this line here. Okay. And if we project, so this is acceleration is somehow here. We don't know yet which is magnitude, but we know that it's perpendicular to this line here, because centripetal acceleration to this is 0.
Oh, okay. Yeah. So I flipped it.
Okay. Yeah, but we also know that if we project this guy here to this line here, then we obtain this centripetal acceleration here. So we have triangle like that here. And this here is the unknown acceleration. But if we project to horizontal, then we obtain this. Now, where is our 30 degrees? So if I would say this here is 30 degrees, right? And so it says that A equal to that A centripetal divided by cosine of 30.
Oh, okay. And cosine of 30 is 2 over root 3.
And then this
or root 3 over 2.
Equal, then this equals v squared divided by 2L and multiplied by 2 divided by square root of 3. which is v squared divided by ln square root of 3. Okay.
Okay.
Mister, can you repeat how you got the direction of the how it is the perpendicular to the second hinge?
Once again, repeat your question.
How the acceleration is perpendicular to the second hinge?
Because this we concluded from the by considering this frame of reference in which this point here is at rest. So, which means that frame of reference which moves with velocity v up. If we go to a frame which moves with velocity v up, then this point is at rest, and then this would draw a circle. This joint point would draw a circle around that. So now, if in lab frame it moves along circle with respect to this, but then now it will move along circle around that center here. Now, so that the centripetal acceleration now onto this line here would be v squared divided by 2l. But the velocity of this point now is 0 because in lab frame it moves with v up, and we go to frame which moves with v up. So relative speed is 0. So in this frame now, where this point is at rest, this is at rest too. And so centripetal acceleration is speed squared divided by radius, but speed is 0, so it is 0. So centripetal acceleration is 0. So which means that acceleration when projected to this line gives 0 projection, which means that it must be perpendicular. Only if it is perpendicular, give it 0.
Oh, okay.
Now we solve the second part.
Yeah, and the second part we already solved. It appears that second part gives exactly the same answer because the situation will be just symmetric. It will be just symmetric because angular speed is 0 when right link is horizontal. So in the second part, we have right link is horizontal, and then left link is like that under 30 degrees. Because then it is at position. So it's link and angular speed is 0, right? And now this moves with up. But if we go to a frame where this is at rest, we go to a frame which moves with v up. So this is at rest, and then this moves down. So we obtain the same problem here, but mirror reflected. So if we flip it back, we obtain the same problem as before.
Yeah.
Okay, so answer is of course the same.
Mr. Calda, why in this situation the omega is 0?
Once again?
Here, the figure you draw. Why the omega is 0 here?
When this no, why it gives you 0? Okay, yes. Because okay, if this bar here is a little bit that way, then this link here cannot be horizontal. It will be either that way or the other way, because now the distance. This distance here is as large as possible when this is horizontal. If it is not horizontal, it is less. So this link here being horizontal corresponds to the uppermost position of this link here.
Okay, cool.
I think you can also see it as because in that position there will be no centripetal acceleration, which means that there is no rotation around the point.
Yeah, you can
so like reflecting it back to the first problem.
Yeah, exactly. You can do that way as
well. Next problem.
Yeah. Okay. Next problem. So do you want to have one more problem on which is similar to this, or shall we go to next type of problems?
One more.
One more like that. Okay. Okay, then we make like that. Also hinged problem. Okay, now this is L, this is L, and this is wait. Just a moment.
If it was like this, wouldn't it be the same as the last problem, just like reflected?
Yeah, something like that. This moves with velocity v up, and at which moment now I ask the acceleration. I already a little bit forgot how this goes. Just a moment, I just to be sure I can check. It should be also in my booklet. For some reason I cannot find it now. Well. And it's most up. And I think something like, okay, this is, let this be fixed, and here is hinge, and here is L, and here is L, and this is directed so that the distance, if we continue this, the distance between this line and this fixed point here is L/2. Is good enough figure? Maybe I redraw. I redraw the figure just because it is not maybe clear enough. So here is a link. Here is another link. This is L. This is L. Now, this point here is at rest. Now this moves. So we draw now a line which is at distance L over 2. So this distance from here to here is L over 2 of this dashed line. And this point here moves along this dashed line here with speed v.
It is perpendicular to the.
Yeah, and so you put here a point, and then you'll draw a line which has distance L over 2. And then you let this
What is the angle?
here move along this dashed line with constant speed v. And then you ask what is the acceleration of this point here at this moment when this distance here is also L. Okay?
The point,
So
the rightmost point is fixed.
This point here is fixed.
And the line, is it perpendicular to the first rod?
This line is also fixed. It moves along this line. This line
Is it
goes at distance L over 2 from this point here.
is the distance L over 2 horizontal, or is it parallel to L, to the first rod?
There is no horizontal. This is just a fixed point. Yeah, you can say it is horizontal. If you like, you can say it is horizontal. Yeah.
Yeah, just. Yeah. But because like, is there is L over 2? Is the distance L over 2
so you have
parallel to the first rod?
You have a fixed point here, and then you draw a line which is at distance L over 2 from that. And then this point here moves along that line with constant speed v. This is L, and you ask about acceleration at the moment when this is also L.
Wait. So the distance L over 2 is perpendicular to the tangent, the line. The trajectory of the.
Mr. Cad, is the line perpendicular to the segment?
You need to figure out this by yourself. So here is a fixed point here. Okay. Now here is a hinge. If somehow you start. Okay. So now you draw a line which is at distance L over 2. Okay. Now you have here one link, and here is another link. And this here moves with speed v. Okay, this is L, this is L. And now at this moment here, which is drawn here, this distance is not L, right? It's shorter. But you are asked to find the acceleration A at that moment when this x is L. Okay. Acceleration at that moment when x is L.
Okay.
Mr. Kala, I don't understand what half L is.
You don't understand what?
The L over 2. What is it exactly?
This dashed line distance from this. So this point is here, you draw vertical line. Then there is another vertical line that is the cell vector. This end point moves along that line.
Okay.
Mr. Kal, I have an answer.
Yes.
I get 2v squared divided by the square root of 3a.
Same for me.
Like that?
Yes.
I think this is correct. Who else got this result?
I get the same.
Okay, you got the same. Okay, yes, that's correct. Will you continue now with this until others also finish?
Just a moment.
Can you repeat what you just said?
Sorry?
What did you just say? You
I
asked
was
us-
saying that those who got this result here can continue with your own problem.
Okay.
Teacher,
Yes.
will you explain problem the blue problem?
Yes.
What's the problem?
Okay, blue problem is like that. You have a rubber band of length 1 meter. And then you are pulling the left end of right end is fixed. You pull the left end at constant speed 1 meter per second. But here on the rubber band, there is an ant which crawls at the speed of 1 centimeter per second. The question is if this ant can reach this wall here, the fixed point here, or not, and if yes, then how long it will take to reach that point.
What does rubber bump? Did you say?
Rubber band you can just infinitely stretch. You are stretching it. You're pulling this end at constant speed.
So the whole system moving.
This end here is fixed. Right hand side of the rubber band is fixed. Left end you pull at constant speed 1 meter per second.
Is it can it be stretched?
Sorry?
مطاط هذا الربر.
Is it made out
أيوه.
of rubber?
مادة.
Like some stretchy material. So it's stretching is what he's asking.
Yeah, it is stretching, always stretching, becoming longer and longer and longer.
Okay. Now clear.
Mhm.
The speed of ant is also 1 meter per second.
Sorry?
The speed of the ant,
Yeah, is 1 centimeter per second.
1 centimeter. Teacher,
Yes.
this speed of ant relative to the rubber.
Yes, right. Now, what about the problem here? How many of you managed to solve it? 2v squared
I
divided
think
by
I'm
square root of
close.
3. Sorry?
I think I am very close.
Okay.
I think only Hussein maybe finished it completely. Maybe Sadiq.
Okay.
What?
Mr. Khadr, can we now have another thing?
Once again?
Can we do a new thing now, like a new problem or something like that?
Yeah, the plan is now to solve this also very fast, and then we take new topic. Okay.
Okay.
So let us do it very fast now. So first thing to notice is that once this here is L over 2, then and if this is L, then this is 60 degrees, right? This is L, this is L over half, so here is 30 degrees. Okay? If this is L over 2 and this is L, so this is 30 degrees.
The top one must be horizontal.
Yeah, and if this is L, so this is equilateral triangle, so this is 60. So this plus this is 90, which means that actually this line is horizontal.
Yes.
So let us redraw it that way.
I finished the solution right as you were about to start.
So let us draw it that way. Okay. And now,
Yes. The velocity of the first one,
yeah,
first hinge must be.
Now, because this is vertical, so we now conclude that this rotates, so the direction of this point is vertical. So because this is also vertical, so this must also have the same speed v. See, here v and here v. Because this is not stretchable, so projections must be respectively equal. So directions are the same, so magnitudes must be also the same. And now we pretty much arrive at the previous problem, with the only difference that we have instead of L, 2L, we have L now. So now here, this length is L, so we just repeat the same steps what we did before. We see that first to conclude that that this point here moves along circle here with a centripetal acceleration v squared divided by L. And then we conclude that if we go to frame where this is at rest, so this is also at rest. So at this moment, centripetal acceleration AC is 0 here. So which means that the acceleration must be along this line, which is perpendicular. And we know this component, so it must be like that. And here is right angle, and here is 30 degree. So we see that the acceleration is v squared divided by L and cosine 30 degrees equal to v squared divided by square root of 3L. And that's it. All right?
All right.
That went really fast.
Mr. Calder,
Yes?
the answer for the blue problem is e to the power of 100 minus 1.
Answer to what? To this?
Yes.
How much did you say?
E to the power of 100 minus 1.
That is quite close, probably something like that. Probably something like that. So it can reach, but it will take a long time.
Yes, yes.
It will take really long time.
I have a question. What is U in this problem?
Sorry?
In the blue one, in the blue problem, what is U?
Right now, don't look at it. You want me to solve now this one here? Because
No.
No? Okay.
We have an hour and a half left.
Yeah, okay. All right.
So.
But now we because we finished with this, we take next topic.
Topic or problem?
Sorry?
A new topic or a
Topic,
problem?
topic, yeah, topic.
Okay.
So now problems with okay, which one I take first? Shall we take actually, I noticed you more or less managed to are fine with doing problems with taking derivatives, like problems like that. We have here rope, and then this here as a ring here, and this can go here, and here is another ring. This can slide along this line here, and now what we let us say this angle is here is alpha, and let us take distance between them is L. And now if this moves with down with constant speed v, then what is the speed u here, and what is the acceleration here? Such kind of problem. You have
Can you repeat,
one
please?
rod, another rod at distance L, and then you have a rope here. You have a small ring which can slide both along rope and along the and the bar, so it can move only up and down along the bar. And here is another ring is tied to the end of the rope, and this can also slide along the bar. And now you start pulling it down at speed v.
And what does the problem want?
And you need to find what is the speed of this ring here, and what is the acceleration of this ring here, given L and alpha.
And is the rope attached to the top?
Yeah, rope is fixed here.
Is the speed v?
Speed v is constant here.
Yes, I mean the speed of the other.
U is not v. I don't think U is v. U is different. Probably. Who knows?
Okay.
So do you know how to do this problem? Do you have idea?
We can try.
You can try, but which method would you take?
We can write like some constraints relate v and u, or like the displacement. So v is like y dot, and u is something like y
Okay.
prime.
Okay, yeah, okay, so let this be, let us say, y, and this be x, okay, and this is L, and then maybe total length of rope is L capital, and then write down some equality, and then start taking derivative, something like that.
Yes.
Did every one of you get the idea how to do it? Or I need to explain?
Yeah, we can.
Ah?
I think we should try first. Try it alone first.
Okay.
Mr. Calder,
Yes.
I'm confused. Could you please explain the problem again?
Explain once again.
The problem, because I'm confused.
Okay. So you have two rods which are fixed at distance L from each other.
Okay.
And then there are two rings, both of which you can freely slide along the rods. And then you have rope. Rope is fixed to up a point here. And then it goes through this ring and it is tied to the other ring.
Mhm.
And then you start pulling the right ring down with constant speed v. And we ask, what is the velocity, what is the speed of this ring here and acceleration of this ring here at that moment when angle here formed is alpha?
Okay. Mr. Calder.
Yes.
Now the rope has two parts. One has a length L and the other has a length X. Is it right?
No, L is total length. L is total length. L capital is total length. Yeah, but there's two parts. One is X and the other is L minus,
Okay.
L minus X.
Okay. is the speed equal to v over 1 minus sine alpha?
I don't know. I can check. So, do you want me to start doing it?
Yeah, I think I got.
I am at the end, like last line.
Okay, I start doing it quietly, and then you can also check and compare.
But v over 1 minus sine. Sorry, it's 1 over 1.
Okay, I got a solution for you.
Okay.
It's do I say the answer that I got?
Yeah.
It's negative v times cosine alpha divided by 1 minus cosine alpha.
Okay. Okay, I started solving it, and I'll see what goes out.
I got the same as this.
Sorry?
I got the same as this expression.
Okay. And now,
Shouldn't it be?
now the trick is to express these things in terms of alpha, right? So
Yes.
if we take the reciprocal of this, L, let me write in different color. L divided by y minus x is okay. 1 divided by cosine alpha, right? 1 divided by cosine alpha. Y minus x, yeah. And then we have still y divided by
I think
y minus 6.
I think there's an error.
L minus
The expression
Minus sign there must be.
there should be x in the denominator.
Sorry.
I think there's an error with the denominator.
Yeah, that's right. So
because this is the same as what I got.
Yeah, because I was expressing here x dot, and I think x dot has y here. Has got y here.
Teacher, minus sign in the second equation. It must be because this is L minus x all squared, not L plus x. When you
minus 2xl.
It was minus here. Okay, let us test step by step. This here is L minus x. So this squared is L squared plus y squared minus 2yx plus x squared is L squared. Okay, here is minus. Here is minus.
Yes, yes.
Here is minus. Okay, here is minus, and then this is minus. Also rest stands, but here is minus, and then we have y minus L. Y minus L it will be. Okay. Y minus L. Is that right?
Yes, yes.
Y minus L. Now, still L divided by y minus x is 1 divided by cosine alpha. And then we have y divided by y minus 6. So we have y divided by y minus 6. Y divided by y minus x. Now y minus x is quite okay thing what we want to have, but y is not that good.
Mr. Calda,
Yes.
I think I got the same, but it was v over 1 minus sec alpha. So maybe if we try to transfer 1 minus sec alpha to x and y, we'll get the same thing, I think.
I think if we introduce more variables, it will make it easier. Like y minus x, you can call that h.
Yeah.
That will make calculations simpler.
That's actually, yeah, it is possible to do that, but I agree that actually this way it is better, easier to follow what is going on. So let us do that way. That we say that y minus x, y minus x. Okay, why not denoted by h? And then we just plug in all the things which we would like to have. So we have this triangle here, which is y minus x, and it has L small, and then actually we are okay with that L capital. No, we are not okay with L capital. Okay, my mistake actually was that I also myself now got confused between L and L small and L capital. Yes. L capital is total length, right? So
also
actually, yeah. So we write it now like that. We rewrite it now like h divided by, and now we subtract and add L small, so that we can have L capital minus L small. Yeah. So we have now.
Isn't L capital equal to? Isn't L capital equal to x plus some like the length of the?
And we also
like the distance between the 2 points.
We also denote L minus x as having L naught. Okay, and this is L naught is this length here. Okay, and then and then we plug in and we have h divided by, and now now we have.
No, wait. It should be L plus x. L plus x equals L naught. I think. What is L naught?
Minus x. L naught is this piece here.
Oh, okay.
Okay. And then if I express now here L capital as L naught plus 6, then I have here in the denominator y minus 6, which is h, and then goes L naught, L minus L naught, H divided by H minus L naught. Okay, and then times V. Okay, and then this equals to I divide numerator and denominator with H, and they obtain V divided by 1 minus L naught divided by H, and L naught divided by H is 1 divided by cosine alpha to minus 1. Okay, which you can rewrite if you like, V cosine alpha divided by 1 minus cosine alpha. Okay?
Yes, very nice.
Here must be, we have to add minus sign. Because minus cosine alpha, 1 minus 1 over cosine alpha, then minus sign to arrive to this expression, isn't it?
Yes, it should be V cosine alpha divided by cosine alpha minus 1.
Yeah, so yeah, okay, with minus, yeah, okay. All right,
Yes.
so y minus x, and over there is y minus L, yeah, minus L naught.
Just the last step only.
Because you make the common denominator. So cosine alpha minus 1, and you.
Oh, yeah, okay. Yeah, if I bring to a common denominator, yeah, so it is minus, yeah, okay. It is minus, yeah, okay.
Yes, because it is going to move upwards.
Right. All right. Now, this was about speed, but now about acceleration.
Take the derivative.
Now we take another derivative, yes.
Oh, yes. Fun.
And this expression is still very precise, no problem with that. We take another derivative here. So we obtain, do you want to do it yourself or to?
First ourselves.
Okay.
Just mathematics.
First yourself, okay.
No.
No need.
Go ahead, sir. No need.
Okay.
Derivative. Other problem?
Sorry?
Other problem.
Problem?
Yes, another problem.
Yes.
Did you find acceleration now?
Just taking a derivative for this expression.
Yeah, and did you get the answer? Did you get the answer?
No.
No. Okay, then please obtain result, and then once you've done, then you get no new problem.
Mr. Calda,
Yes.
why don't we do it together?
Okay. Everyone agreed to do that we do it together?
Yes.
Okay. Now those twos go away. And then we have y dot squared plus, but keep in mind that y double dot is 0. Okay? Because it moves with constant speed. So this guy here has constant acceleration. Y double dot is 0. Okay, formally we will have y double dot, but this goes away. And then minus, again, y double dot, which goes away times 6, minus y x dot. And then from here, we have minus y dot x dot minus y x double dot equals minus x double dot L. Y dot is V. So we have now V squared. V square now minus y times u. So Vx dot is u. Y times u. Wait, something is wrong. Y double dot. Okay, this term here cannot be, derivatives don't match. So this is first, this is second term. This is derivative of second term. It's y dot x dot. Okay, and y dot x dot, and here is also y dot x dot. Okay, yeah, so these match, and we have two of them. Okay, now two y dot x dot. 2y dot x dot is 2 u times v minus 2u times v. And then there is, now let us bring this to right hand side. This equals a and y minus L.
What is the first term in the left side?
Here,
V squared.
V squared, yeah, because it's y dot squared and y dot is v. Y dot is v, so v squared from this term. Y dot x 2 times, y dot is u, x dot is v, the other way around. And then we have this term, which is y times a, and here is L times a. This goes to the right hand side. And so we have a equals v minus 2u and divided by y minus L. And now we can plug in u, of course, and now we can plug in y minus L, with which we have already expression, I think. Okay, now we need to work a little bit on it. So y minus L. What we need to now, basically, we have v, we have u, but we need to work on y minus L. So y minus L, but we had our quantities. Y minus x is h and L minus x is L dot.
Teacher.
Yes?
We can hear see U equals L over tan L small over tan alpha because we have at this moment, and we can find y minus L from the upper from U equals.
Yeah, from here we say that y minus L is H minus L capital. And H is the distance here. So we need to express everything in terms of L small. It is L small multiplied by, now if we speak about H, then this is cotangent alpha, yeah? L times cotangent alpha. And minus L capital 1 divided by sinus alpha. Is that right? L naught, this length here, is this divided by cosine. This divided by sinus. This side here divided by sinus. 1 divided by sinus alpha equals L, and this is cosine is is it correct now?
Sir, I think the rest is just mathematics and
the rest is mathematics. Yeah, I agree. So basically,
yeah.
And
I think it could be long if you simplify it too much.
Whiteboard is full. Actually, we could finish. So we have y minus L, which goes to here in terms of L, and then we have v and u here, which goes also here, and then you just need to simplify. Everyone happy with that?
But I think it's correct because it's the same as my solution. So
okay.
Yes, next problem.
Yes, happy.
Happy.
More than happy.
Extremely happy.
Okay.
I have a question about the blue problem, bottom right. What is U?
What is U?
Yes. What is its value? No, in the not this one.
Blue. 1 centimeters per second.
1 centimeter.
1 centimeter per second. Yeah.
And this is how fast the
ant moves.
The ant moves. What about how fast the rope stretches?
Yeah, 1 meter per second.
Okay.
Mr. Khalda, this U is with respect to the rope.
Yeah, with respect to the rubber.
What's now, sir?
What's now? Now we take another topic, and now this is going to be the ballistic problems. When you throw a ball on the gravity and how it moves. Okay. All right. So now if we throw something, or maybe before we go to that, we can solve few other problems. Still.
We have 45 minutes left.
I know, yeah. So maybe the ballistic motion and optimal trajectories and things like that will be for tomorrow. And today we take problems which involve the main idea of which is considering things in a free-falling frame of reference. Problems in which case you can consider things in free fall frame of reference. And so one problem, I think it was Estonian-Finnish Olympiad, something like that. Something like that. We have a photo is taken of two pieces which have been thrown from point P. Point P on the ground, and then there are two pieces, one of which at certain moment of time is here, and another is here. Okay, maybe the point. Okay, this is like point P is on the hill, maybe something like that. Okay, here you have hill. At point P, you throw two pieces with the same initial speed at the same moment of time. So this piece here and this piece here have been thrown exactly at the same moment of time from this point P with equal speed. All right. And then, based on this figure, you are asked to find what was the initial speed if, let us say, 1 meter is this length here. You have given here scale, 1 meter. Okay? And what is the initial speed V? V naught.
Are they thrown different angles?
Yeah, sorry?
Different angles, the initial.
Yeah, they are different angles, but the same initial speed V naught.
And what we have, and what we have to find?
Initial speed with which it was thrown.
What is the line that passes through the point P?
Sorry?
What is the line that passes through the point P?
Both pieces were thrown from point B.
Yes, there is a line that passes through the
This
point
is
P.
like slope, like a hill. Point P on a hill.
Oh,
because,
so it's,
yeah, because I was looking that this is already below the horizontal line, so I just in case I drew a hill. Not important. The shape is not important.
okay. But what is it that we know about this?
So we know that there is a free fall acceleration g equal 9.8 meters per second square, and you are given scale. This length here is 1 meter.
Are they thrown at the same time?
Okay.
And this is photo taken from this side. Okay.
Okay.
Was they thrown at the same time?
Yes.
Mm-hmm.
Okay.
Yeah, both pieces were thrown at the same time. Now will you try to solve it?
Yes, we want.
I don't think we can like get a numerical value if we don't have the actual question.
Yes, every question is going to be different because of scale. But we can we just find it using values instead of the thing?
Yeah, just what is important here is the method. And it is not important what the numerical result will be, but the method, how you calculate. This is important. This I want to know, how you do it. What you measure and what you calculate.
Do we know the velocities at this point, at this time?
No, you just know the positions.
Okay.
The positions are on the figure.
Do we have any information about the horizontal line? Or
This line is not important. Direction of G is given.
oh, okay.
G is straight down.
I think I have an approach. Like we know the equation of the trajectory. Okay.
Once again?
We know the equation of the trajectory. Okay. Like y equal to x tan theta plus the rest. And we have an equation for the displacement along the x direction. From that, we can find we could find the angle. We could express the angle in terms of the time and the speed, and substitute it in the original this trajectory equation of the trajectory, and then we will have an equation that include the time, the coordinate, the x and y X and
well,
Y.
it's too complicated. And besides, I told you that the problem is going to be on using free falling frames. So the hint here is consider this everything in a free falling frame.
If we went to that frame, the distance between P and the first object, it will be equal to the distance between P and the second object. And we will have a triangle that we can calculate its length.
Okay, we go to a free falling frame, and how moves the pieces, the two pieces in that frame? Once again, clearly, how the two pieces move in a frame which is free falling?
Right.
Straight line.
Straight line. They both move with straight line with constant velocity.
But we also have like the whole thing moving, not only so like the hill will also move.
If we are in a free falling frame, then there is no gravity force, no acceleration, because well, we can add acceleration, right? So in free falling frame, one piece moves a straight line and the other moves a straight line. And here is VT and here is VT. So they are always at equal distance from the point where when they started. Okay?
I mean, but doesn't like point P also move?
Yeah, but point P is at rest in lab frame, so point P moves up. So this was point P at the beginning, but in our frame, our moving frame, free falling frame, point P moves up. So now P is here at distance, GT squared divided by 2.
Oh yes, and the distance between P, and all the other bodies is going to be the same. So P is like relative to P, it's like it's normal. So you can take another P prime at the origin.
Mm-hmm. So basically, we need to find. So now the question is, where is this point in this figure here? How do I find this point here in the free falling frame from which they were thrown?
We can find the intersection of the two trajectories of the 2 points along like along the perpendicular line.
Okay. So first we know that this point must be a vertical line, right?
Yes.
Because P is moving in our frame straight up. Okay. So our point P prime is on this vertical line on the one hand. On the other hand, it is at equal distance from this and this. And so all the points which are on mid perpendicular are at equal distances, right? So we take this segment here, draw a mid perpendicular, and we extend it. And that's the point when those two intersect. So this is the point, okay? Agreed?
Yes.
Yes.
So how you proceed? I build mid perpendicular, draw vertical line, find intersection, and this is our P prime. Now point P moved up, and so this distance here is GT squared divided by 2. But we now we measure this distance in meters, comparing with this 1 meter scale here. We calculate this, and then we calculate now time t. We can calculate from here t. And now this distance here, which I can also measure, this is V naught times t. And now this is that L, and so V naught is L divided by t. We just measure this and divide it by this t to obtain initial speed. Okay?
Okay.
Mr. Khalda,
Yes?
from where did you take this problem?
Sorry?
From where did you take this problem?
This was originally Estonian-Finnish problem. I made it myself.
Yes.
Which year?
I don't remember exactly, but I think it should be also in the booklet, in the kinematics booklet.
Okay.
All right. Now, one more problem on free falling frames.
Aren't you going to do the math for this or not?
Sorry?
Aren't you going to calculate it numerically?
This one?
No.
This one.
Problem.
Well, I think once you got the idea, I think it's the rest was just measuring and calculating. It's not so interesting, right?
Oh yeah. Okay. Okay.
Okay. All right. And now, what was the problem here? We have here two balls, and this is also. I think this is booklet problem. I need to check what was asked actually. Configuration is like that, but I better check. Okay, so you release at the same time this ball and this ball. And this travels down during time t1. And this travels down during time t2. And now you ask at which moment of time the distance between the two balls was minimal.
What is this triangle? Again,
okay. This is a slope, angle alpha. Another slope, also angle alpha. Like one plate, another plate. Okay, here this starts sliding down, and this starts here sliding down at the same time. No friction. And the time required for this to travel down is t1. The time to travel down here is t2. And the question is, at which moment of time the distance between them was minimal? Between this and that. Okay, this moves down is here, this is here, okay? Now this is here, this is here. At certain moment of time, the distance between them, it starts decreasing and then increasing again, the distance between them. Here the distance is, this distance is here, and here it is distance here. Somewhere there is a distance was minimal, right?
Yes.
Travel time here t1, travel time here t2. When was the distance minimal?
This is the whole question.
Sorry?
This is the complete question. Nothing is only T1 and T2.
Only
And
T1 and T2 are given. T1 and T2 are given. And angle alpha maybe also. Who knows?
Okay.
Angles are equal here and here.
Oh, never mind, never mind.
And here also idea is to use not exactly a free falling frame, but free sliding frame. So you go to a frame where one ball is rest, one of the balls is at rest.
So initial velocities are 0.
Yes.
I think I found the answer.
You found the answer?
Yes, it's a very intuitive solution, but I think it's correct.
Okay.
Do I say it?
So what is your answer for T?
Oh, wait. Oh, you want the time? Okay.
Yeah.
Never mind. Okay, I need to find the time. I found something else. The angles are the same, right?
Yes.
Or not?
Yes, angles are the
Okay.
same.
Okay.
Because I have a solution.
You have solution?
Yes.
Very good. Can you tell me answer?
The square root of t1 squared minus t2 squared over 2.
Okay, let us see. Shall we solve it together?
No, just a moment, sir. Only 3 minutes, please.
Okay.
I found another solution.
Yes.
T1 minus T2 divided by sine alpha.
T1 minus 2 divided by
Sine alpha.
sine alpha. Now,
I got the same as Hussein.
sorry?
I got the same as Hussein.
Which
Me
one?
too.
This or this?
The up.
First one.
Yes,
First one.
the square root. Yes.
Okay. All right, let us solve it. So what I do is I go to a free fall sliding frame. Let us say this is at rest. This is at rest. Okay, so our frame is moving down with acceleration g times sinus alpha. Okay. So yes.
I got the same, but in the denominator, also the square root of 2, not only just 2.
Square root. I think here it was square root, so it's just my writing, bad writing. Okay. All right. So we go to a frame which moves down with g sinus alpha, which means that if we add accelerations, then we need to add to everything g sinus alpha the other way around. So if this here moves down with also with g sinus alpha, in our frame of reference, we need to add to subtract this thing here, which becomes now a vector like that. Okay, and by addition of vectors, we obtain here horizontal line. So it moves horizontally with acceleration. Now, if here is alpha, then it moves horizontally with g sinus alpha cosine alpha 2g sinus alpha cosine alpha is the acceleration, which happens to be g sinus 2 alpha. Okay, not that we will need it, but anyway, we have.
Isn't it? How did you get the acceleration here?
First, when it moves down, acceleration g sinus alpha, do we need to derive it? If ball slides down, it moves with g sinus alpha acceleration.
No.
No need for G sin.
No need. I also think no need. No need. This moves down with g sinus alpha. Now we go up to a frame of reference in which this ball is at rest. So translational accelerations can be added just as velocities. If system rotates, then we need to take into account different accelerations like centrifugal acceleration and Coriolis acceleration. But in the case of translational motion, we just add acceleration in the same way as velocities. So now this moves down here g sinus alpha along the slope, but our slope, our frame moves down that way. So we need to subtract this vector, which means that we need to add the opposite vector. We need to add vector which is up here. Now we have isoscale triangle, which means that this here becomes now horizontal. This is also alpha because psi equal angle psi equal. So it moves up horizontally. This ball here moves horizontally. Okay. And now we need to figure out how long. Now it is clear where the distance is minimal. Distance is minimal when it reaches this point here, which is directly balanced, because our ball is at rest and this moves horizontally. Closest point is when it is straight behind, below, straight beneath. And now we need to figure out how to express this in terms of T1 and T2.
You can find them.
I found an error in my solution.
Sorry?
And I corrected it. I found a correction to my solution. It should be square root sine alpha instead of sine alpha. Square root of 2, I mean, square root of 2 sine alpha.
Like that?
No, square root of 2 multiplied by sine alpha. So sine alpha is outside.
Okay.
Teacher,
Yeah.
is the final answer going to be square root of T1 squared minus T2 squared, then divide by sine alpha? Or sine alpha will cancel. So it will be just sine alpha.
Guys, let us try to finish this and then we'll see what it is. Okay. We are already running out of time, and we have this problem here as well. So let us try to finish this, and then we'll see. Then you'll see what is correct and what is who has got correct and who didn't get correct. Okay.
Okay, go.
Mm-hmm. So we can see that it will be a straight beneath when it is the shortest distance is when it's straight beneath that ball here. So that
we can find the length, sir, and then use.
Sorry?
He said we can find the length.
Yeah.
And then use sine alpha. And this will be.
Okay. Now about time t1. Let us say that this distance from here to here is L1. And the distance from here to here is L2. If this falls down, so it's G sinus alpha, the projection to horizontal direction is G sinus alpha cosine alpha. Now we have L1 is G T1 square G sinus alpha cosine alpha. T1 square divided by 2. Is that right? If this distance from here to here is L1. And L2 similarly is G sinus alpha cosine alpha T2 square divided by 2. So now L1 minus L2, which is what? L1 minus, if this is L1, this here is L2. So this piece here is L1 minus L2. Okay, so L1 minus L2 is G sinus alpha cosine alpha divided by 2 and T1 square minus T2 square. Now, this is on the one hand. On the other hand, this ball here travels horizontally with speed 2g sinus alpha cosine, acceleration 2g sinus alpha cosine alpha. So until the moment when it is at the closest distance. So now we have that L1 minus L2 is G 2g sinus alpha cosine alpha T squared divided by 2. So everything cancels away except for this coefficient 2, so that indeed T is, this is correct answer. This here is correct answer. Okay, can you see? If I express here T, then I obtain that.
How did you express it? Like, where did the sine and cosine go?
Sine and cosine were here and here. Okay, this 2 was here. And
okay.
G goes away similarly. Only
okay,
this coefficient 2 here it remains.
Okay, but I have another a question. Why wouldn't the because what I did is that I said that it will be when it's horizontal, which means when the horizontal distance between them is equal to 0. I mean, when the distance is only vertical. So I measure okay, I will redo my calculation and I'll see.
Yeah, okay. Now, everyone fine with that?
Yes, yes.
Now, there are plenty of problems where you can use these free falling frames. We'll see how much time we will devote more. Maybe we had enough of exercise. I hope you got the idea how to do it. We had 2 different scenarios. One was that our frame was just free falling, and the other one which was sliding. Okay, we have two options basically, and now you need to be just creative to figure out when you need to apply that. And once you know this idea, you should be able to solve many otherwise difficult problems. Okay.
Okay.
Now, shall we try to solve this problem here?
Yes.
Yeah.
Is it long or?
Sorry?
Is it long or?
Well, we have 6 minutes. It depends. Maybe 10 minutes, not more, I think. Maybe 10 minutes. We can start just doing and see how long it will take. So here, actually, the main idea, how to solve it. Of course, you need to write down certain integral. But the main idea here is, okay, how to express the progress of the art. It is somewhat difficult. So the main trick here, how to parameterize. So here is important. What is important is good parameterization. If you take physical distance, you run into very long and nasty expressions. But because the progress clearly for the ant is expressed how much of the rubber band remains behind. It starts from the point when there is no rubber band behind, and it ends up when all the rubber band is behind. So it's kind of clear that the best way to parameterize the progress is what fraction of the rubber band is left behind. Do you agree?
Yes.
So actually, okay, let us say that x fraction of rubber band left behind. A fraction of rubber band behind. Okay, and now you just need to express how this evolves. So at certain moment of time t, the length L of the rubber band is L naught plus Vt. Okay, so that now dx, yes?
It's again.
So dx over dt is now the distance which it crawls during time dt is u times dt is distance traveled, and divided by the current length of the rubber band, which is L naught plus Vt. More or less fine?
From the beginning, please.
The unit.
You want from the me start from the beginning?
There's a problem with the units, I think.
Sorry?
There's a problem with the units.
UT, I think, like
U is the speed of the endpoint. So U is the speed of the ant. So ant with respect to rubber band travels U dt.
the units don't match.
Oh yeah.
Yes. Yes.
What
I think it should be U plus something. Yes.
Let me see. U dt is distance. So yeah, I'm missing here one time. Just in dx is u dt divided by that right here and divided by. Okay, let us write that. Let us just remove here dt. Okay, now happy?
Happy.
Okay, dx is this. And then we can just integrate. X is integral u dt divided by L naught plus Vt is now, if we take integral here, it is u divided by V logarithm of L naught plus Vt divided by L integration constant. If we put here like divided by logarithm of 0, then at t equals to 0, this goes to 0 and x is 0 as needed. And so now our equation from where we obtain the answer, we start with x equals 0 when t equals 0. Then we have logarithm of L naught divided by L naught, logarithm of 1 is 0. So yes?
I still think that there's an issue with dx because it is equal to a unit of meter divided by unit of meter, or distance divided by distance.
X is dimensionless.
Okay.
It's fraction of the rubber band behind.
Oh, what does it represent?
Sorry?
What does x represent?
X, I started explanations that it is in this problem. It's very important to find good parameterization. Our parameter x is what is a fraction of rubber band? What is the percentage? Which part of rubber band is behind? And so x starts from 0, no rubber band is behind, and ends up with 1. The whole rubber band is behind. And as it crawls, so it this with respect, it moves with respect to rubber band to the distance UDT. And the program fraction, this makes of the fraction of the rubber band UDT divided by current length, which is L naught plus VT. Current length of the rubber band is like that. So the fraction which is behind changes by dx, which is distance divided by the length.
Yes, I get it now.
And now integrate, obtain this, and we start from x equals 0 when t equals 0, and we end up when it is finished scrolling, then x becomes 1, and so we have u divided by v logarithm of 1 plus v and travel time t capital divided by L naught, so that t equals now L divided by V
E to the power of
E
to the power.
Sorry?
And then e to the power of v over u.
Yeah. Then e to the power of v divided by u. And then what? We need to subtract something. So minus 1.
No, minus.
Right.
Okay.
Yeah.
Yes.
That's it, right? And that's it.
Okay, good. Mr. Khalda, I have a question regarding the idea of changing the reference frame in order to calculate the tangential acceleration. From where did you get the problem, or from which source can I use in order to see
this problem? This problem. Sorry. This problem is a very famous problem. I think I don't know. Remember exactly which Russian academician went to the meeting of Russian academicians, like the top brand of the Soviet physicists. It might have been Zakharov. It went to the meeting of Zakharov and proposed this problem, and none of the academicians were able to solve it.
Mm-hmm. I mean, what about the problems related to the idea of changing the reference frame to calculate the tangential acceleration? From where can I see problems like that?
Oh, a certain set of problems is in the kinematics booklet. Now, I think I don't think, I cannot give you right away, like I collected such kind of problems into the booklet, at least part of them. And then,
so there's not, is there a book like related to ideas? Because we know the concepts, but there are some tricks that we are not used to.
I have tried to collect all the ideas, all the tricks into the into my booklets. So just open the kinematics booklet and there you are.
Okay.
Okay. Time is up, so I have to go eat dinner.
And we are finished also. So tomorrow, 4 o'clock.
4 for us and 3 for you.
4 for you, 3 for me.
Okay. Then.
Okay.
See you.
See you.
When are you going to upload?
Sorry?
When are you going to upload the lecture?
Yeah, I'm going to upload. It is going to be converted, and once it's converted, then I'll upload. This might take some time because it is 5 hours of lecture, so compressing it will take some time. Okay, I think I'll give you next time when we meet. I can just into this chat here. The same link which you had today works also tomorrow. And so just join on the same link tomorrow, and I'll give you here in the chat window the link. Then by then I think it should be ready by then and upload it.
What did you say? Are you going to what?
Sorry. Well, it will be you want it earlier, the link, or I just can send you by email then the link once it's up.
I mean the link for the sessions on YouTube.
Yeah. Otherwise, I can just we had the previous training session. I can just use the same playlist and add up over there to that playlist.
Okay.
Okay. All right.
All right. Goodbye.
Thank you.
Yeah, you're welcome.